Welcome to the fourth lesson, CE 5361, Surface Water Hydrology. And today's lesson will be on the topic of watersheds. The first part will be a PowerPoint presentation like the other lessons, and then the latter part will be the demonstration of making measurements on an already delineated watershed. And speaking of delineation, all the methods discussed in my lessons are as if you do not have access to modern software tools to do that work for you. So if you have a GIS and appropriate shape files and appropriate digital elevation maps, it's far easier to delineate using those tools than it is to do it by hand. But I'll go over briefly how one would accomplish this doing by hand. I mean really just on a computer doing image interpretation. If you had to in some future instance, which might happen if you're working outside the United States and those digital elevation map coverages are of insufficient resolution or perhaps don't even exist, but topographic maps usually do. The other advantage of knowing, or at least having done it manually once, is it gives you a good understanding of what's going on inside the machinery, because the methods that computer employs have to be very systematic for it to be successful. And there's things we as human beings can do that we don't even think of. Oh, nothing's working right today. This is just one of those days. Log out of that. I do not want to be logged into the website while I'm trying to use it. It tends to cause mistakes. Teaching. I've been trying to get that stupid sidebar to go away for weeks now. It's just ignoring me. Go to the Moodle site. But I'm not logged in there. Surface Water Hydrology. And this one I will log in as an administrator. And it will take its sweet time. I got a phone call from my internet service provider that they're willing to give me free upgrade to fiber as long as I pay for something else. So the modern definition of free is not what I grew up knowing it as. Go to course content, and I have kind of two motives for doing it this way. One is to get used to. Second one, I'm going to go lessons. I want to go to lesson 3, which was yesterday briefly, because I've been doing some. Okay, it's a half done. So the data links in yesterday's lesson turned out they're only on the Moodle site, and because the way it's programmed, you only get 10 visits to the lesson. I'm trying to transfer them here, but you may or may not be able to perceive this. They're in a different format. So I was working on that this morning. This is not at all correct yet, but at least the URLs are there, so I'll be able to finish that after today's lesson. Today is watersheds, which thank heavens there is content. Yes, there is. And the data will be I think that's everything. Oh, it's almost, I got 2 left to upload. So in addition to offering me a free fiber optic upgrade for an extra $100 a month, maybe that'll make this faster. I don't trust them. I think they're just trying to hustle me for money. Okay, so having said that, grave revelation, let's begin the lesson. I'm going to take the latter dated file and hope that that's not a mistake. We'll know in a second. Get to the end and check. I think that's the correct one, but I might as well be sure. Since this is live, we don't get to do it over again. Let me check my localized copy. Get a date on that. Oh, that's what I was afraid of. For some reason, selected the wrong file, and I currently can't do anything about that. So I'll use my localized copy. I will upload the corrected file. Looks like the Moodle images is what I had intended. Okay, so we shall proceed. Today's topic, watersheds, watershed delineation, and watershed metrics. Okay, so the watershed is the functional unit of surface water hydrology. So watersheds can vary in size from very small, like your driveway, to basin scale. For example, the Mississippi River Basin. And other than those sizes of those two being vastly different, orders of magnitude different, certain elements of the two are common. They both have a contributing drainage area, an area to which a drop of water, if it falls somewhere on that area, will eventually get to the outlet. They all have a concept of slope. They all, for a large extent, will have a concept of a main channel, although it may not always be full of water, but there is a path that predominantly carries water from the interior of the watershed to the outlet. They all will have some concept of a transverse or side slope. They all have a concept of path, and they all have cover materials, whether it's the driveway, which is largely concrete, except for my driveway, which is cracked like my cell phone screen. So it's mostly concrete with bits of grass tufts poking through, to the Mississippi River Basin, which, even though there's been a large amount of human development over several hundred years, as a basin, it's probably mostly natural covers, or at least bare soil covers. It's a soil with trees and plants and other growing things in it. And although there's probably substantial concrete, when you consider the scale of the basin, the amount of surface area that's concrete would be relatively small compared to the total drainage area. So we have a definition of watershed. I'm pretty sure I've used this definition before, and from time to time I'll reuse it again because everything's spelled correctly. I hate to throw away a perfectly good statement. No, we'll use it again as a matter of reminder. One definition, the one that applies to most of the situations in this course, would be the topographic area that collects and discharges surface stream flow through one outlet or mouth. And that's called the pour point in at least the older GIS jargon. I don't know if it still uses that word or if they have something else now. And then a similar definition that is a little bit more extensible than the first one is it's the area on the surface of the earth that drains to a specific location. That second definition admits the possibility that we can receive water at a specific location that didn't necessarily get there topographically. It may have taken a storm sewer to get to that point. Essentially, it has its own topography that it's adding a third dimension to the concept. Generally speaking, I would argue that topographic area and actual drainage area to a point, for the most part, are going to be very similar. Even in a highly developed urbanized setting with a lot of storm sewers, a good predictor of water flow path will be the topography. We can ignore the groundwater concept entirely because I'm not going to discuss that this class. But when you see the word watershed, the UK version of the word is called a catchment. It's the area that catches rainfall. When you see those, and then you see the word groundwater basin, they largely mean the same thing. It's the area that all the water contained in that area gets to some discharge point. So the next process that's important in a watershed from a surface water hydrology point of view is how to determine what a watershed is. And so this image behind me, my background image, is unfortunately not quite how I intended to look, but it's an already delineated watershed, and we'll actually look at that very map later. And there's these little red flow lines on it, and so on. This one is. Oh, this is actually the correct orientation. So this side's west, and this is east. That's north up by the top of my head, and south down here by my neck. We're going to, in this lesson, we're not going to actually create these lines. I'll discuss how it's done and try to point to some of the steps that were taken to create it. But we will examine how to measure these different areas. So the first step, which is to create this outline of the watershed, the 4 points down here by my left shoulder, is called delineation. And for doing it with electronic tools, such as ArcHydro, what it needs us to do is to identify the pour point and provide it with a digital elevation model or a digital terrain model or a triangular irregular network model of the elevations. And through a variety of internal algorithms, it will determine on our behalf what the boundary is of that watershed. So one of the techniques I know that the old ArcGIS used to do, so this is back circa the 1990s, so it may have changed, is it's pretty trivial to have the GIS program go to a cell, an XY coordinate on the map, if you will, and determine how many cells are uphill of it in a hydrographic sense. And that's called flow accumulation calculations. And then we arbitrarily determine that it's a river cell if the flow accumulation is... Hope you're laughing at that. That's one of my cats who's decided to help us out with the lesson. He is not very good at watershed delineation, but he's really good at laying down on keyboards. At least say hi to the people. Come here. I'm going to let you see. Okay. This cat's name is Nico. Nico, look up here. And he's waving at you all. Okay. And for those of you who don't know, Nico is Japanese for cat. So when I call him Nico the cat, I'm really calling him Cat the cat. It keeps people away from the house, which is generally handy, but I mean, I'm doomed if I ever call 911. It's like, it's that crazy man who's got the cat. Okay, back to where I was. I'm not going to edit that out. This will at least make replaying the video for you all somewhat humorous if you haven't fallen asleep yet. So it can count flow accumulations to a location, and then it does that for every location in the map. And we pre-specify a certain number that if it's larger than that, that's declared a river cell. And when it gets to the pour point, the algorithm at the pour point, the flow accumulation count should be huge. And it works its way from the pour point up the flow accumulation network to a certain cutoff that we prescribe. Maybe we use a cutoff of 30, which I think would be awfully small on the GIS side, but nevertheless, once it gets less than 30, it puts a boundary at that point. and ultimately it can return the polygon that describes the external boundary of the watershed. That's one technique. Another one that I've used that's a little bit, well, it's quite a bit slower, is to arbitrarily place tracer particles on the digital terrain map, let them move downhill according to any kind of kinematics you want. Getting the speeds correct is irrelevant at the boundary delineation step, and keep track of the origin of the points that pass through a particular point. So from fluid mechanics, that's called a streak line. It monitors the streak line to a point, that point being your outlet, and then it returns all the cells that got to the outlet, and then you have to go beyond that to get the watershed boundary polygon. That's automated, and we do the same thing if we do it by hand. So I'm going to illustrate some steps for manual delineation. These are intended for folks that have never ever had to delineate a watershed. So if you've never done it, even in an undergraduate class, or if you've never had a hard one to do, these would be a good starting point. Now, a skilled human being can skip or reorganize quite a few of these steps, namely the first one, because we can do something a computer program can't, which is to look at a map and not have to superimpose a grid and start counting along grid cells. We can see a high spot relative to an outlet point, identify that, make a mark with a pencil, and move on. And so relatively small watersheds, a map of which that could fit on your kitchen table, you can usually do faster total time involved than a computer can. I mean, the computer will beat you once it has the digital terrain model loaded into it. But if you have to go find that model and provide it to the computer, you kind of lose there. Whereas if you have a map, you have a digital terrain model on the map. So the first steps that I would propose to someone just learning how to do this is to superimpose a grid onto your map. That's as simple as taking a piece of plastic, put it in your photocopier, photocopy a engineering grid paper so that what's on the plastic is clear and then black grid lines. I would advocate against drawing directly on a paper map. You won't break the map, but they get wet, you spill coffee on them, you lose them. Then once you have the grid, you can estimate average elevations inside each cell of the grid. You don't need exact, you just need average. You know, is the elevation 1,070 feet or 1,030, pretty much on the average inside a grid cell. And that works pretty good, except in the area of a very steep elevation change, like cliffs. And then you'll have to make a analyst judgment decision, but that's not usually a problem. I mean, there's plenty of cliffs in the world, but they generally form watershed boundaries that are kind of favorable in delineation consideration. And then once you've found the grid, I find it useful to outline the main stem of the stream that you're going to examine. And I literally draw that, again, on the plastic part, but you can do it directly on the map. And then the perennial, the influential tributaries that go into the stream. And I tend to put little arrows on which way water would flow if I was water. And then finally, from the outlet point, we're going to work our way uphill to delineate our watershed. So here's an example. This happens to be in Florida, I think in the Orlando area, but I'm not positive. I know it's in Florida, and it's kind of hard to imagine that Florida has elevation changes of 100 feet. Here's some contour lines. So these are level sets. It's representing a third dimension by contour lines. So here's contour line labeled 200. Here's one labeled 100. It has these little tick marks that means that this is kind of a lake edge. we have a scale down here, which is it's pretty important that if you're doing this electronically or using photocopying, that you copy the linear scale with the map. Because knowing that this is a 1/24,000 is completely useless for this image. I have no idea how many times that image has been increased and decreased in size. But as long as this linear scale right here is carried along with every increase and decrease in size, this distance right there, measured on this map, is always going to represent 1,000 feet on the Earth. We're also told that there's a contour interval of 10 feet. So each of these brown lines represents a 10-foot change in elevation. And that's pretty handy to know because it saves you from having to count between labeled lines. Sometimes you have no choice to do that. So let's take a look at this as human beings right now. Here's my outlet. The cursor is following a path up what appears to be a stream to this point, and we go a little further. In this spot right here, there's an elevation of about, there's a 200-foot line and a 200-foot line. So we have two elevation lines that are close to each other. They don't cross. So at this point somewhere here is bigger than 200 feet. But as we're coming from where I am right now with the cursor, I'm moving uphill, uphill, uphill. Now I'm on what passes as a plateau, and I'm starting to drop downhill. So there's a divide in watershed behavior somewhere in this region. Water on this side tends to flow that way. Water on this side is going to go that way. And we essentially want to identify all those points along the boundary. And here's our outlet point. We have a road along the outlet. And if we were to look at the outlet itself and want to go uphill to the south from the outlet, the fastest way uphill is going to be, that was not the way I went to go, that's the pen, it's going to be like that. And we'll get up to this high spot here. And now we want to join high spots. That's not right. It goes over here. Okay, so I'm not attempting to do a really good job right there. But I'm just illustrating as human beings, we actually can usually identify high spots quite a bit more efficiently than a computer, because we have several thousand years of evolution that make our pattern matching algorithm in our brains good at that. But we want to start with locating the outlet, which is done. Then I think it's useful to sketch a light grid. So here's a grid that's been superimposed, and it's not perfect. Perfection's not necessary for what we're going to do here. And then what I would do in each of the grid cells, along what looks like a boundary to me, is I would identify the elevation. So this one's maybe got an elevation of, well, there's a 100 line right there. Maybe call that cell 100. I look at that one, it's probably about 150, and label the elevations, the average elevations in those cells. That will help me find the high elevation. And I wouldn't do the entire area. I mean, it should be evident when you've done enough. So if the elevation along one column or one row is going up, 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 and then starts going down, maybe go two more down, and you're done for that column, and that will help you identify the high points going on around. So here, that's been done. So it's going uphill here. So what I perceive is going to be the boundaries. It's actually going to follow this road for a bit, and then it's going to pick up all these high spots. And those red cells constitute our first guess of the boundary. These red lines are hand-drawn representations of the tributaries. I'll modify them slightly, although I think the next slide gets it. And water, say up in this corner, is flowing that way, down this tributary. So you use this elevations and the path lines to help you identify what the contributing area is. Once it gets to the lake, it's not very interesting. So we have flowing downhill, it goes into this lake. It looks like if it's in this lake, it's got to go that way somehow. Oh no, that's coming into the lake. My bad. And if we look here, there's path line going that way. You don't need to overdo it, but drawing the path lines helps you interpret what is and what is not watershed relative to your pour point right there. So here it's done. And at this point, we can go back through and start to draw a boundary. Now, I would certainly admit that probably right in that region, that doesn't look quite right to me. It seems to me more that the boundary, let's get a different pen color for fun. Ooh, magenta, that's just such a fun word to say. Seems to me more like the boundary right here does something like that. I think this corner is excess area that tends to go that way and not towards our outlet. But that's a refinement step. Initially, we've got a pretty rapidly determined boundary outline. And now that we have the outline, we can draw that onto our map, and there is our watershed delineation. So I guess this area here in this corner was kept because the analyst, that was me, determined through aerial imagery that this road constituted what would behave as a dam or a levee, and there was no cross-flow structures to get water to the other side of the road, so it has to flow along the road to the lake before it can go out the culvert. And that level of interpretation is necessary a lot of times. So you make your initial delineation and then do some manual refinements as necessary. Computer programs don't necessarily have that knowledge of whether there's cross-flow structures or not, so they also have to be refined after it does the initial delineation. So there's our watershed for this particular example. And then the red lines are identifying the major tributaries or flow paths. And then if we wanted to define a main channel, we would probably choose this one, which is the longest path, and declare that the main channel. And one important metric of watershed is the length of that channel. Another important metric is the elevation at this end and the elevation at that end, the difference between those two divided by how long the channel is. That's called the main channel slope. There's also a 1085 slope, which represents the difference in elevation, 85% of the length of that channel upstream and 10% of the length of that channel upstream. So you see 1085 slopes a lot in hydrology work. One can argue whether they're meaningful or not. They've been used for several hundred years, well, at least 100 years. And then we could consider transverse or slopes along different paths. Okay, another tool that can be used is something I recently learned about called Stream Stats, which is a USGS product. And the URL is shown right here. And what this is a map server of the United States, and you can go to places on the map server. You don't actually draw red circles. You click on a spot, and it makes a little widget doobie bopper. And you can use that to have the map server identify a drainage area to that point. So we'll just use this Oklahoma portion as an example. If I can quit pressing the wrong buttons, there we go. So this circle, excuse me, this circle lies in a stream that's crossed by a project culvert. We can't see it at that scale, but if we zoomed in, there's a creek right there. And let's say we want to know the drainage area to that circle. using stream stats, we identify the location. You can see I've zoomed in quite a bit, and we select the basin delineation object, and it draws this little yellow representation for us. And I'm not sure it does that live. I think it does a database lookup, which is actually pretty incredible from a computer science standpoint. So now there's this yellow area. Well, that's nice. Our next step is we can export a shapefile bundle of this yellow area. In this instance, the shapefile is kind of a misnomer because it's not a single file. It's a bundles of files that describe information in that yellow area. Within that yellow area, some of the physical metrics that are typically available from stream stats are the outlet elevation, precipitation, historical precipitation values, including an annual mean value, which has some significance in regression equation application for hydrologic uses, a composite soil permeability, 1085 channel slope, mean basin slope. Those are based on the 10-meter digital elevation model. And just as important, that shapefile provides a boundary file. So it's a polygon boundary that can be used to extract an elevation raster from the National Elevation Data Set. So using that boundary in the NED, we can actually extract a digital terrain model. And then once that digital terrain model is extracted, we can make other metrics on that. And the available coverages of stream stats are shown in this map. This is circa 2019, last year. So the green areas are fully implemented in the stream stats map. The blue areas are going to happen someday. The magenta has delineation and basin characteristics only. I forget what basins means. Entire basins. I think these are the ones that are, let's call them in progress for lack of anything. And the states that do not participate are Texas, Florida, Oklahoma, Kansas, Nebraska. That's got to be Michigan. They're currently not participating. So not participating means the stream stats project will take your state's data and put it into their tool. And the privilege of that you have to pay for. It's kind of like we're going to build a dog park, the best dog park in the world, and the cat's going to pay for it. So these states have not paid into the program yet to have their data represented in the program. That's happened before. For example, in Texas, NOAA Atlas 14, Volume 11, which is Texas, it had been showing up like this for the better part of 2 decades before Texas finally scratched together the money to pay the National Weather Service to put their rainfall data into the precipitation frequency data server. And although that was a lot of money up front, now it's there, and now it's federalized, which means the state no longer has to maintain various databases. It's up to the federal government to do that. And I think it's a one-time chunk of money. So when you look at it amortized over a lifetime of data service, that's probably a pretty good bargain. So for the missing states, for the time being, they're not going to get there anytime soon. The data exists because it would be extremely inefficient to run a federal agency and have very elaborate map server coverages and then cut holes out of it just because states don't pay for it. But they're not providing it as part of the program. So the data are undoubtedly archived at the USGS and will become available when the various non-participating states come into the program. Here's a couple of our references. If you're interested in stream stats. I dabbled with it not too long ago. It's pretty cool up until you get the shapefile bundle. Because my the GIS I use when I use it is called Quantum GIS. It could visualize it just fine, but I had a hard point trying to pull the ASCII grids out of it. And that's not the program's fault, that's probably me. I also wrote some R scripts with some help that can process the shapefiles. So it's a pretty cool tool. And all other things being equal, if you don't have to do it from a paper map or an electronic equivalent of a paper map, by all means you should use these tools that are available. And they're outside the scope of this class. Bottom line, the automated tools pretty much do the same thing that you would do interpreting a topographic map. They're generally faster. They're not necessarily more accurate, but they're of equivalent accuracy. So why do we do all that? Well, as I said before, the fundamental unit in surface water hydrology is the watershed, and it's a pretty important conceptual unit. Some of the minimal properties that are important for watersheds are the area. In fact, area is the scaling unit. Two watersheds, otherwise identical, if one has 10 times as much area as the other, you expect that one to produce 10 times the response for the same rainfall input. And that's only obvious. I mean, it's 10 times bigger, so if 1 watershed inch of rain comes in on, let's say they're in acres, for 1 acre watershed, you have accumulated 1 acre inch of water. If that 1 inch of rainfall comes on our 10 acre watershed, you've accumulated 10 acre inches of water. So in volumes alone, the area is extremely important. And it's been used as the scaling unit for watershed hydrology probably for the better part of 200 years, maybe longer. The other important property is main channel length, even if there's no permanent stream in the watershed. Slopes, those require specification of path, and then soil moisture or cover behavior and the permeability. So the area affects the catch, how much volume the watershed can catch. The main channel length, to some extent, reflects the time response of the watershed, how long it's going to take things to get to the outlet. The slope is also going to provide information of time. Steeper slopes, things would be expected to move faster than on shallow slopes, other things being equal. And then the soil moisture and permeability is going to affect the infiltration capacity of the watershed. So main channel length and slope and area deal with volumes and time. Soil moisture deals with one of the two major loss components, the other one being evaporation. And the slope also is going to convey, to some extent, some information of on-watershed storage, that depression storage that we discussed earlier. What I don't have listed here is the vegetative cover. That's not a metric that's easily obtained from map-type data. You have to use aerial imagery for that. But most of the fundamental processes can be largely explained or largely correlated to just a handful of watershed properties. Hence, the delineation and measuring the properties is pretty important. Okay, so here's those repeated again. I must really like that slide so much I use it twice. And here's the watershed that's currently behind my head in the video feed of me. And in other past classes, I've used this as a in-class exercise. I don't actually know how to do an in-class exercise electronically, so we're not going to. But in this one, there's 4 points of interest. And in class, as a workshop, I would hand you a 11 by 17 printout of this, which is about, it's pretty big. I mean, it's not super big, but it's pretty big. And these squares right here I think those are 1 mile. Let me check with the vertical scale and my highly calibrated. Yeah, these squares are mile squares on this map. So we have most of the information that one could expect from a map. And I believe on the in-class exercise, I do this one using an overhead projector and start drawing the boundary, and I work up along the highway to about there, and then I kind of follow this undifferentiated area to that high point, and there's another one up here, and so on. And then the classroom people are tasked with the behavior coming out of this riser pipe on this dam. So there's a dam here, and that encompasses this area over here. And then these two are actually pretty easy. Those are done as homework. Okay, so and we use the method I just described before: superimpose a grid, get average elevations at grid intersections, starting from the outlet, work uphill to the high point, and then move along the high point to identify boundary. And comp stuff looks like this. So the next step is how to determine things based on those drawings. The important things would be the area of the watershed and the length of the main channel length, and we'll explore that in a minute. We have 2 possible main channels on this one. And then the soil coverage and vegetative cover are done with independent tools, but still working on that area. So I'm going to stipulate that you all can get to this point. So now we want to get to how to measure things. So there's left column represents the various approaches. One technique, I gave it the generic name of numerical planimetry, and it involves various software tools. So ArcGIS, you can do these in AutoCAD by measuring polygon areas. AutoCAD is probably the worst tool for doing hydrology work because of what it is and what it's designed to do. It can be made to do these things, at least raw AutoCAD. I'm pretty sure there's add-ins that handle much of the hydrology for you. It's not worse than doing it. It's better than doing it by hand, but not much. Acrobat Pro, if you still have access to the old Acrobat Pro, it has measuring tools in it. So you can handle measuring areas and lengths quite easily in these tools. A commercial program that's for making surface plots called Surfer also has measurement tools built into it. Engage, which is the one I had intended to use for this class, I'm no longer able to get it to work correctly. I mean, it still works. It loads the graphics, it loads the drawing tools in, but they're not working right. And I can't tell if it's a setting that I've failed upon or if it's something that's broken over the years. And the last one is something called G3 data, which is strictly a digitizer. All it does is produce XY coordinates on top of images where you specify a coordinate system. With those XY coordinates, we can put it into something called polyarea, which is an Excel spreadsheet that does a polygon area calculation, or we can do it in R. And if we have enough time today, I hope I'll be able to do it in R. There's mechanical planimetry. Normally I show my mechanical planimeter, but it's not here at the house. It's a rather confusing looking device. It has wheels on it and little connectors and springy things, and it performs the same tasks as drawing a polygon and integrating it for you. And then the last method, which is sort of funny in a broader context, which is to superimpose a grid of squares and count squares. You know how big each square is, and you count the number of squares contained in the watershed to get an area, and you count the squares that follow a path line to get a length. It's kind of funny because that's actually what a computer is going to do on your digital terrain models. Is a a last resort measure. It's a very slow technique, but it's guaranteed to work. Now, tools to measure lengths. Here's another set of the same software for measuring lengths. Also measures areas, and then by hand. Measuring length by hand is actually fairly easy. Then once we have those two metrics, finding soil properties, we can do it using this tool called the Web Soil Survey. To start the Web Soil Survey, you press on this green button. Nowhere on this web page does it tell you press on the green button to actually do something useful. Instead, it tells you all about the Web Soil Survey. So I guess the rest of the world knows to press on green buttons to start things. I always like to press on the blinking red button, although it does tend to make your spaceship explode to get started. Or old-fashioned soil maps. So let me exit the presentation and I'll have to go slow when we go to the server. Naturally, the upload failed. Okay, so what I wanted to do was good. I have some tools available. Let's go take a look at the base map that's behind my head. That was stupid. Let's do it this way. So here is the watershed of interest that's been delineated already. You can see the little red arrows indicating flow paths, and somebody's done some artwork to indicate where the streams might be. This particular watershed is located near Eden, Texas, which is out by San Angelo. I can pretty much assure you way out here in these remote parts of the catchments, there's no water. Certainly not right now. Well, maybe there was good rains yesterday, but not really right now. And then this Brady Mountains from people out from the West Coast, or the Appalachians. These are not mountains by your reckoning. Okay, so someone has done the activity of delineating the watershed, and we may want to determine the areas in each of these catchments. So there's this one that's labeled the Eden catchment, North catchment, and West catchment. And we're going to be revisiting this example throughout the semester, so let me spend some more time describing some things. The West catchment is defined by this dam right here and a riser pipe that drains the dam. So the West catchment corresponds to this reservoir, if you will, and all the area that drains to the reservoir. And that reservoir is connected to HARDEN branch of this creek and makes its way over here and eventually flows out here. And this is our point of interest, is there's a culvert right here. The North catchment similarly is controlled by a dam or regulatory structure. So all this area here drains to this reservoir before it makes its way on downstream here. And then the Eden catchment captures all this area. These two red dots happen to be major culverts on a highway, and flow will come here, make its way into the main stream and to the outlet. And so then the Eden catchment includes the two contributions from the North Reservoir and the West Reservoir, as well as all the area intermediate from either of these two blue points to the outlet point. So it's taking the flow from this small city as well as these flows. So this is a study area. Somebody has already delineated it. You'll also notice in the image that there's little itty bitties. There's a rectangular grid that's superimposed on the image. And the grid orientation, clearly there was no attempt to line it up with the XY coordinates indicated by these mile squares. And that's okay, it's actually not necessary. And the grid is big enough to be able to see, small enough to be useful. And so what we could do is we know that, I don't have drawing tools on that, do I? Yeah. I don't think I have the ability to draw on this image. I do not, so I'm going to have to allude to how to do it. If I had drawing tools on the image, I would attempt to draw one of these mile squares. And I know that the area contained in one of these squares is 5,280 feet squared, whatever that is. That's a big number. Then I would count how many of these little squares are contained in one of the big squares. So I use this one. This one's good enough as an example. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 11, mostly 11. So I'll go 11 in that direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's more like half of 11, so 10 and a half. So there's 11 by 10 and a half of these small squares contained in a big square. So I make the multiplication, that'd be 110 plus about, there's about 116 small squares contained in a big square. So now I have 5,280 feet quantity squared equals 116 little squares, or each little square is 1/116th of 5,280 squared. So now I have a conversion factor. Then I can determine areas of these odd-shaped areas by simply counting how many squares is in, none of this is small enough to get away, is in one of these odd-shaped areas. And I have another image that shows that completed. I think it's good, they're uploaded. I think it's scan 1. I hope that downloads and renders. I didn't think of that. So what I'm illustrating is the counting square technique, the somewhat most tedious of the manual techniques, but very much how a computer works. And like computers, we have to download stuff, and I hope I got the right one. And it's here. We'll open with so here's that counting squares worked out on a sheet by hand. So what the analyst did here is did the easy stuff first. All those completely contained squares, didn't bother to count those because they knew that those were 1 square mile by 1 square mile. But in this corner here, each of the little dots indicates the number of little squares contained in that area. And then in this one, we counted up that area, then he counted up that area, then that area. This one they took a full 1 square mile and subtracted out that area, added in that area, subtracted out that area, and added everything up. And then when converted to the various units, I believe they have 16.93 square miles of drainage area. Let's take a look at what scan 2 is, although we may not need it. Well, that's a big one. Okay, so an alternative to that, I want to go back to that picture. It's 16.93 square miles. I'm going to try this again using a tool called the G3 data. And what we can do is we can digitize that boundary. And then once we digitize that boundary, we can calculate the area contained in that boundary in generic units, and we can also compare that to the area contained in a 1 mile square. This is pretty useful. So let's take a look at the download. Okay, so scan 2 is illustrating using counting squares to get lengths. And so the analyst has counted all the squares that constitute the two main channel lengths. And this one here is roughly 7 miles long, that path. This one's 5.2 miles long. So the main channel length in the usual context is going to be the longer one. So we declare main channel length is 7 miles. The elevation at this hilltop is 2,190 feet. The elevation of the outlet is 2,010. So we do 2,190 minus 2010. That's 180 feet. Divided by 7 miles would give us our main channel slope. And we also can get the slope along this path too. Since we have the path, it's worth getting that slope. And then those will be used in subsequent hydrologic analysis for modeling the behavior of this watershed, if you will. So how much of time? So what I'm going to do in the next 10 minutes, I'm going to go to the Share Hydro. I'll digitize this boundary. And that's, I think, all I'm going to be able to get done in 10 minutes. And then offline, I'll go ahead and digitize one of these areas, and I'll leave behind an R script that calculates the drainage area for you, and I'll pick that up at the next class meeting. So let's go to Share Hydro. Wrong one as usual. There we go. Actually, I've been using Hydro 3 for most of my development work because it has a different color background. And the program here is called G3 data. And what we need to do is get the files. So I'm going to go to lesson 4. Data, and let's see, the one I want. You can see there's some other watersheds here. We'll pick those up next class meeting. Let me go ahead and get, does it work on JPEGs? I think it works best on JPEGs. Let me go ahead and download that one. Save link. And it should get there pretty quick, because this is going server to server. It doesn't have to pass through my internet service provider. Simplify that. Downloads. My bad, I made a mistake. G3 data defaults to a directory contained here. I'm going to go ahead and create a new folder. It's actually a bad folder name because it's not really Concho Creek. It's in Concho County. Verify the base map is there. Okay, it is. Now I'll go ahead and I'll launch the program. And if it's going to work, takes it a few seconds to load. It was working yesterday. I'm going to go ahead and center this. So this one is a little tricky because it has very limited, frustratingly limited real estate. So now I'm going to attempt to open that graphic file. So I need to go to G3, Concho Creek, choose the base map. It's rendering what I think it is. If I open it at image scale 1, it's going to completely fill the screen. I know from trying earlier that 1/10 is about the right, gives me a workable size. Perfect. Okay, so now we need to identify X and Y coordinates. So we're going to go to that. And what I find that I want to do is I want to try to keep the entire watershed in the upper right quadrant of an XY coordinate system. So I'm going to put X all the way over here. I'm going to give that a value of 0. X2, I'm going to put, that's like 5,000, that's 1, 2, 3, 4, 5 miles, which is 20,640 feet. So I'll put that there. I probably should move that down one. 26400. Now for Y1, I will put it back here. I'll set that at 0. And then Y2, it's going to be 1 grid cell down. So there's 1 mile, 2, 3, 4, 5. And we'll go 1 click up. So 26,400 feet. So now we've identified a coordinate system, and we're ready to I hate it when it does that. We've got to redo the coordinate system. This is one of the flaws of free software. At least I can do it correct this time. Remove all points. Go to that one. Put the point. X1 is 0. X2, 1, 2, 3, 4, 5. It is 26,400. Y1, 0. Y2, 1, 2, 3, 4. 6,400. And now we're ready to start digitizing. So you notice as I'm moving the cursor around, the XY coordinate system, the XY of the cursor is changing. And so to digitize the boundary, we just start dropping points on it. I'm actually going to make a very crude digitization on purpose so that when we try to drop it into a spreadsheet program, that's the only thing I have working on. I don't have an R script. It would take a couple hours to write an R script. Probably won't take that long, but I got to get it debugged. So I'll do that external. and I try to drop that second point on top of the first. I don't have to get exact. So there's our first boundary, and then we can export it to a file. We'll just save it back in the Concho Creek directory. That first one we just did was the Eden catchment. We'll change the extension to TXT so it doesn't confuse. So I hit export, boom, done. We'll go look at that in a minute. Actually, we'll look at that right now. Okay, let me shrink this. So I may crash the program, but we'll hope that we get luckier than that. And go here, go to example 1. Let's go to the right one. Concho Creek, Eden catchment. And we now have XY coordinates in our coordinate system for determining areas. So we will put that into a program that integrates polygons. It's 11 minutes after 10, so I can't do that live. So what I'll do is I'll make a recording, and I'm going to pick up from this point, from these data files, and complete the watershed analysis. I'll put that into a video, and I'll post that when I post this live video. So that's as far as I want to get today. The digitizing program has uses far beyond measuring watersheds. You can use that to take graphs out of journal articles and produce XY plots from them. You can pass functions through them. As a, for instance, example 1, is this plot, and what was necessary was to obtain a formula for this line right here. And it's easy for these straighter ones, but when you have these lines with some curvature, being able to digitize that and then pass a function through it was beneficial. So that's what this particular program is good for. Okay, so with that, I am going to check that nobody sent me, good, nobody sent me a chat message. I will open this up for questions, and you technically have enough to do the last part of the first exercise, which is to delineate the watershed. That will be comparatively easy, and make the necessary measurements using, if you need to, use counting squares technique. Depending on how fast I can get this video out on how to use the digitizer, by all means, that's easier for you, the human being, to use. It makes fewer mistakes than counting squares. If you have access to a GIS and want to use it for that exercise, by all means do so. And if it's okay with you, if you do that, when I get the exercises and look them over, for those that have done it by ArcGIS or a GIS approach, I'd like to clip some pieces out of that and share it with the class. So I'll contact anyone that does that directly by email and get permissions to extract the GIS approach to share with the rest of the class. So are there any questions?
Sir, when I was following along during lesson 4 on mine, and I got to the questions part, one of the questions, like all the answers that's saying it's wrong, it didn't take any of the answers.
Oh, I will take a look at that and fix it. Okay, so check question 4, lesson 4 answers. And it's possible that I programmed it wrong.
Right, because I mean, one answer says that's right, it could be used to delineate, but it still says it's wrong.
Oh, you mean it won't let you move on?
Sorry, what did you say?
It won't let you move on to the next part of the presentation?
Oh, I can move on. It just keeps saying the question's going to be wrong.
Okay, I believe that particular one has two answers. And let me go ahead and get to it. Okay, lesson 4. I think I know what you mean. It may not be clear.
I didn't realize I could put two answers.
So I'll go through this as fast as I can. Actually, wait a minute. I have edit capability. Let's see if I can get to that. Was it after the stream stats or is it the last one? It's the last one, right?
Should be. It's like the very first question. It's like midway into the lesson.
Midway, then it must be this guy. Manual delineation. Let's see if it'll let me preview it. Let's see, you need to answer contour plot and map. Let's see if I can go ahead and replicate. I think preview is the tool I'm going to use. Okay. So I don't want to edit it. I want to preview the question. This one, right? Is it this question?
Right, that one.
And I continue. And I don't get grades because I'm the administrator, but that's what was looked for, was those two a physical map or an image and a contour plot from elevation survey. The other possible answers are not relevant for manual delineation.
Right, thanks. That worked. I just didn't realize I could put two answers.
I usually say multiple answers in the actual question statement, so that's a mistake on my part. I apologize for it. And everybody watching the video will be able to do it correctly. And again, don't sweat so much the grades on the lessons. Even a grade of 0 means that you look through the lesson, and that's all I'm going to use. I'm using it as a way of taking roll, to be quite honest. So the lesson grades themselves aren't going to play much of a role at all in the course grade. Your homeworks and the quiz grades, other than quiz 1, which also is not going to be used in the final grade, it's just to be sure you can take the quiz. They matter more as a, what do you call it, a participation score. But as these issues come up, feel free to raise them, because I'll try to make some corrections and see if it will let me edit this right now. So it's manual delineation. Let's see if it's going to let me edit the thing. So it is letting me edit the thing. Okay, so that's one thing. So that's the response. This will fix it. Okay, so that should allow the necessary okay, so that doesn't change. And then we would put contour plot. We'll just do one of them. And it says 2 of 2, so we're not getting the whole set of answers. That's implying that there's more than one answer. So we'll stick with that one, and it allows us to continue. Okay. So that was my intent on how it was supposed to perform. So thank you for bringing that up. Are there any other questions? Well,
I guess one more question.
Okay.
Do you expect us to finish exercise 1 before Monday?
I'll put the video out on how to do the digitizing using G3 data by later today, and I think it's doable by Monday, but if there's desire to have a little more time, that's pretty trivial to change. I'll do that right now, in fact. We'll make it due Tuesday. That should be... Oh, rats. Somebody already submitted. I may have to... Oh, wait, that's me, so that's okay. I can do a override. I also want to change the time. So we're going to make it due Tuesday. And Tuesday at midnight would be Monday night. So I'm going to do Tuesday at 5 o'clock. Hit save. Okay, Tuesday, June 20th, 5 p.m. Now, one issue is I don't know if the server is on Central Daylight Time or if it's on Zulu, Greenwich Mean Time. Because, like I said, the server's in Europe, so unless I've overridden that and told it to localize time, it's giving the European time, which is 7 hours difference. So this might be due at 10 in the morning on Tuesday if it's on European time. So given that that's possible, let me go ahead and get it at a decent time. So let's see, if I do it at 11 at night and it's European time, 11 minus 7 gives you 3, it's 4 in the afternoon. Okay, so we're going to go with that. And that way I'm covered whether or not I have the server time set correctly. So it's due at 11 o'clock on June 9th, which is a Tuesday. And that will give us Monday. If there's questions on Monday, they're having difficulties, we can take some time on Monday and address how to do that problem. So that was good that you brought that up. Thank you. Are there any other questions?
Dr. Cleveland?
Yeah.
Just to clarify for number 6, when delineating the watershed, would you like that, because it says manually or using the G3 data?
G3 data is manual, but you can count squares if that's easier for you.
Okay.
It's doing the same thing. Let me go to your question. Yeah, it says this is intended for manual if you have access to automated tools and the DEM. So this comment here, that means if you're going to do it in the GIS, feel free to do so. To use a GIS, though, you're going to have to use that latitude, longitude, and you're going to have to find a digital elevation model, which will be on the National Map server. I frankly think it's faster for a one-of to do it just from the image and hand draw it. But I'll let you decide that. And if you choose to count squares, that's fine. If you choose to use the G3 data, that's also fine. You're kind of constrained by me putting a modernized G3 data video up. I have an old one on my website, but you would need a new one. Let me see if I even have the old one cross-referenced. I may be spared. Okay, so this one shows how to do the delineation. This one shows how to use engage, but that's no longer useful. It doesn't work right. The video's fine. The engage is not good. This is a pre-recorded version of this lesson that we're having right now. So I just did not answer your question. Go ahead and use G3 data. If it gives you problems, you can superimpose a grid system and count squares to do that, and that'll be good enough. Unless you make a grid one square, that'd be a pretty good way to game it, but not very useful. That's your backup. Does that give you enough guidance?
Yes, sir.
Okay, I'll try to have a video ready by this afternoon, because I have to upload this video, and once I use up a communication channel, I might as well use them both and then walk away from the computer until it's done. So I will be doing that. If anyone has any other questions, I actually need to terminate the call in 4 minutes because I've gone 6 minutes over class time, which doesn't hurt the video any, but technically you are free to go. So if there's no further questions, I am going to stop my screen share, and then I am going to terminate the phone call. And with that, have a great weekend, everybody, and I'll try to get that video out so you can get this watershed out of your life as quickly as possible and enjoy the weekend. I think it's supposed to be nice weather this weekend, so by all means, take advantage of that. Okay, goodbye, everyone. Have a great weekend.